Okay, right. So um, so welcome to our chapter 2 session today. Today the chapter is basically somehow looking at the basic conceptual of how learning started, deep learning, and some kind of historical background. So it is, I think, in chapter 3, the next chapter, maybe next week, that we'll see how you start training machine learning using maybe scikit-learn and Python. But today is some kind of basic background trying to tell us how um, learning started, how it works. So this as the topic that will be covered in chapter 2, um, the intuition of understanding of machine learning algorithms, how machine learning algorithm works. Also, we will walk through some kind of uh, numpy and stuff like that. And finally, we will implement a linear classifier to do some kind of classification. Um, and also, we'll talk about what is called perceptron, which is what inspired, maybe I can say, machine learning or deep learning, which they compare with the artificial neurons we have. So that is basically what we're going to see today. So if you look at this, the book started talking about what is called artificial neurons. So as you all know, for example, in deep learning, or yeah, what we are trying is we are trying to mimic how neuron in our brain works, right? That is why we have what is called artificial neurons. That is, we are trying to mimic the neuron in brain, right? So these are the guys that try to understand how biological brain works. Warren Merkel and this guy are the first to simplify brain cell, the so-called Merkel pit neuron in this paper. So they were the one that tried to say, okay, the brain works, we can model it. We can use the way brain function and process information to model it, in the sense that we can use maybe computer to model that kind of process. This is how the beginning of thinking of machine learning or deep learning. So if you look at them, this is biological neuron. um, you can see we have what is called dendrite, right? So dendrite are something that receive input signals from outside the wall. And now we have cell nucleus here, which basically try to make some understanding now. These are some axons. Finally, we output something, axons, timeless. So this is something related to biology, or yeah, the biological neurons. So this is biological neurons. So what they try to understand is, so can we model this? Because we know people from medicine or from biology, other field, they have already developed for many years. They understand this, right? How this. But as of today, we have not actually understand fully how brain works. So as of today, even the scientists, they don't actually understand fully the functionality of brains, but they understand some kind of component. For example, this is what they receive information, but they don't know, for example, exactly how brains collect, how brain process and understand information. So this is something that they are still working on. So, but we understand what are the components this receive information, and information flow from here, and you can output something, but they don't understand how exactly stuff works. So this is what inspired other people to come and say, okay, let's design something that like brains, biological neuron. We have artificial neurons, so that we can do something artificial rather than human, which is uh, non-artificial. It does something, but let's design it. So if you look at this, this is something they started. So you can see this is artificial neural. We have dendrite, cell body. We have, this is a human brain neural. This synapse, you know. So you can see this is what we started from this year, from this artificial neuron, I mean biological neuron to artificial neuron. So you can see this is something that we started depicting. For example, this is the dendrite. So these are the dendrite from biological neuron. This is artificial neuron. So here you can see we have um, salvary. Then here we have something like this. You can see that we have something activation function, which reflect accent. Then we have output. So this is basically how this thing started, that they're trying to basically map what is basically the biological neuron to map it to artificial neuron, so that we can be able to follow how human understand information and process it. So can we model that so that computer also understand and model information the same way? So this is basically some of the history they discuss about the beginning of the chapter. If you read it, you will find out this is it. Yeah, any question before we move on, or anyone wants to add something? Okay. Right. So let's see how we can formalize this. So we have seen now how this works. Now, can we formalize this stuff mathematically to see what is happening here? Because obviously, since we are going to use computers, one of the best way to solve complex problem is to mathematically represent that problem and solve it computationally, right? Yeah, so mathematicians, Haji Akuni mathematicians, so you solve every problem computationally. If a problem can be represented mathematically or algebraically, so we can find a way we can model it and solve it. So this is what we want to try. So the definition of an artificial neuron. So these guys, the Warren, McClock, and Walter, they were the one that think first that, oh, we can model human brain as something like this, something like it. But this guy, another guy, Frank this, published the first concept of perceptron, learner rule based on this MCP neural model that they presented, with the perception that algorithm will automatically learn optimal weight coefficient that would then be multiplied. So what he says is this. So given this, this is biological neuron. So if we can model this, for example, he even proved that we can use mathematical formulation of a biological neuron could solve and or not problem. So these are something we know in mathematics, right? And or and not problem. So what they are saying, we can solve this problem with this. So for example, these are our dendrite input signals. This is an example of and. So we can have one here, we can have x1, we can have x2, and now we can have something comes here and we can have something and give us output here. So what is W1, W2? So this W1 and W2, so these are something that we will learn, that if we multiply our input with W1, our another input with W2, and now we sum them, given some kind of threshold that they should not be maximum to one particular threshold, we will get an output. So in learning, these are what we will be learning. Wait, how given an input, because this an input, this is something like this. Oh, I have an example. So give that input is maybe, let me give you an example. So we have maybe data set for classifying flower. We have sepal, we have sepal width, we have petal length, we have petal width, right? This is the class Setosa, Besosa. So given this, given this, given this, then the class is this. Given this, given this, the class is this. Now you can see here we have how many features? 4. 1, 2, 3, 4. So here, for example, maybe I just give 2, 1, 2. So maybe we can have 4. Now, given this 4, what are we going to multiply by this input? That is by this input. This multiplied by another by one weight, this multiplied by weight, this multiplied by weight, this multiplied by weight, and if we sum them, they will give us something. So now the question is, what are these weight that we will try to find out, so that when we multiply them to give us a clear output? So if you look at this one here, for and, we know that if your x1 is 0 and y1 x2 is 0, x1 is 0 and y, when you do multiplication, for example, we said x1 times 1 plus x2, which is 0, times 1, which is will give you 0, right? And you remember this is our XO in mathematics, which define this, right? If x2 is 1, then you are this. If any, it is only if you are doing and. If all of the two are 1, 1, then you have input, you have output is 1. For example, this is 1. 1 times 1, 1, plus x2 is 1. 1 times 1, 2. And now you can give, your output is 1. So these are some of the things, on all those days, before we start doing the Newton. This is just historical stuff that they say, okay, this kind of neuron can be used to solve this kind of mathematical and or and stuff like that. So if you read the chapter 2, this is what they started talking about. And yeah, so it's good to know this. But you can see here, we can represent this problem like x1, x2 up to xn. We can represent them as a vector. So you can look at this. Okay, x1 to xm, and weight, our weight w1, w2 up to wn, we can represent it as a vector. W1, W, can you see we say W is this, X is this, right? So you can see here is W1, W2, X1, X. You can see this is just a single number. But here, what is the difference between W that is bold or X that is bold? Okay, you can see this W is bold, right? You can see this W is not bold, right? So what is the difference? Hello? Hello? Can you hear me? Yes.
That the one that is bold is representing vector.
Yes, exactly. Yeah. So you can see here, this W is a vector and this is a vector, because here we just represent. So you can see here, it means if I have from x1 to xn, I can represent it as a vector. If I have w1 to wn, I can represent it as a vector. Now we want to put this in terms of mathematical expression. Yeah. So now if that is the case, this is what we call activation function that try to map. Yeah, we'll see this. So this is something that activation. This is perceptron, single layer perceptron, something that if the value is greater than 1.5, then classify it as something. If it is less than 1.5, so this is some kind of a function, Cilium function. So here we can see here is that we can put this. Yep. So let me put this in perspective. So this is from the book. If you look at this one, we can say Z equals to W1 X1. For example, what will come out from this? Z x1 times w1 plus x2 times w2 is equal to z. So let me show something so that maybe it can be more understandable. Just give me a second. Okay. Yep. So if you look at this now, how can we represent this information mathematically? This information, for example, if we have n number of x and we have n number of w, how can we represent it mathematically? So let me share my screen. Something. How can we do that, Hadia?
When are the x1, x2 up to xn, and
Okay.
w1, w2 up to wn.
Yes, exactly. So this is what I want to show. So here, for example, yeah, something like it. Z, that is the output of here. That is the output of all here that will go inside here will be something like this. Z equals to W1 X1 plus up to WX plus XM, right? Something like this one here. Without this B, we'll come to this B. I don't know how in Zoom we use something like board, right? Is it board or something like that? I want to see. I want to write. Whiteboard. How do they use whiteboard in Zoom? Okay. Can you see my screen now? Can you see whiteboard?
Yes, we can see.
Yes.
Okay, right. Give me a second. What is my this thing? Okay. Right. Okay. So, oh. Okay. What about now? Can you see my? Oh no. Okay, I see. This I want to share screen. Then I can do this. Okay. What about now? Can you see my screen? Yes. You can see, right?
Yes, we saw one. Is it S small letter
Okay.
A?
Okay. Okay. I don't know how this thing works. I want to. Okay. So if we look at this, anyway, let's just move on. I don't know, like I'm not used to this screen. So what I want to say is this. If we look at this, here I have W1, X1, W2, W2, X2. So if we sum all of these, then we can have something like this. X1, W1 plus X2, W2, right? Up to N is equals to Z, is equals to something like this Z. So this Z is something that will impute inside here. So this is what I want to show. Now, if we look at them here, if Z is greater some threshold, which is theta, give us 1, else give us 0. So this one, the one we, what can you see now? Can you see my screen or not?
I can't see your screen.
So we can see.
I was talking about something.
I thought it was only me.
Okay. Yeah. So what I was saying is, let's continue. I was trying before to show using this, but it means I don't know how to do that. So what I'm saying is that if we look at this input, we have X1, W1, X2, W2, right? And yeah. So we can represent this as something like this: X1, W1 plus X2, W2 plus up to whatsoever. This will give us Z. So what I'm saying here is this: this plus times this times this, right, is give us the results. Now we're gonna input the whatsoever to our step function. So now here step function, we have some value that do some classification. So this is it. If the Z, that is the result of summing this one, is greater than the threshold we have with this threshold, then return 1. That is, it is in class 1. Otherwise, return 0. So what we are doing here for this perceptron is classification of 2 classes. So you can see here, it's classification of 2 classes. That is 0 and 1, 0 and 1, 0 and 1. So here our problem is classification of 2 classes, 0 and 1. So this means that now we have this, and now this is when we apply this unit function on it, we have this. But we can have our theta here, we take it to this side. Here in this chapter, please try to understand, it's given us the intuition when we come to doing other stuff in the later. So it's very important to understand the intuition. Now, if you look at this here, we say Z is greater than theta, right? Now, if Z is greater than theta, what is theta? We have the step function here. So for example, here I have X1 times this plus X is this, then it gives me maybe 2. So when I apply to step function here, my value, my Z is the step function is 1.5. Yeah, it's greater than 2. Then if it is greater than 2, what will happen? Then it's greater, it will be 1. It will be classified as 1. But if my sum of this one is like 0.5 and my step function is 1.5, so we compare that. If Z is greater, no, otherwise it turns 0. So the class, yes, so it's classification of 2 classes. Now we want to generalize. So if Z is greater than theta, we can take theta to this side, right? Mathematics, and take this, so we can see Z minus theta equals greater or equals what? 0, right? Now this minus theta is what we call bias. So for example, now if you are doing some stuff like that, this time this plus this, in any case, we have in general, we have some bias that may influence our external bias. So if you are doing computation, there are some external bias that may influence. So we have some bias that will add to our algorithm. So in this case, now instead for us here that you can see, I say W1 plus up to WXN, WN to give me Z. But now we say, okay, we have something bias we want to add. So let's add something plus B, which is bias. Can you see that? So that's why here you can see we have Z equals W1 X1 plus last one plus B. B is the bias. It's equals to WT times X plus B. Does anybody can answer what is the meaning of how do we get from here? How do we get here? Can anybody? How do we get here from there? Can anybody share?
Yes, can you hear me?
Yes, we can hear you.
Yes, I think this, as said earlier, this W represents the vector.
Wait. Yes.
So here we transpose the is a kind of transformation that we do. Yes.
Okay. Okay. So let me put it another way. Yeah. So if we look at this in this way, you can see here we said Z equals to ana ganin screen ɗina ko?
Yes.
X1 plus WM oh, not this self. Let me remember, this is what we said Z in the beginning. This is what we said. Z is this. We say Z equals to X1 W1 plus X2 W2 plus XN WN plus B, right? B is a bias. Now, what we are saying is that if you look at this X1 plus W1, these are basically some numbers. X1 maybe that is 2 times 3 plus X2 that is numbers, it's 5 times 6. Can you see that? So they are numbers. But what about if we want to replace change this X as vectors? Because if we have this X X1 W1 plus X2 W2, when we want to do this, because this is multiplication, we can replace this as this vector X1 X2, then haka kuma na mu saka W1 W2. Can you see that? So to represent them as a vector. But if we want to represent them as a vector, this means that for you to do dot product, what is the dimension of this one? For example, this is 2 by what?
2 by 1.
2 by 1. What is the dimension of this one?
Also 2 by 1.
2 by 1. Now, can we do multiplication by 2 by 1 and the 2 by 1? Can you do multiplication?
No, it's not possible unless we transpose one.
Yeah, sai mu yi transposing din wannan ko?
Yes.
To idan muka transposing din wannan kun ga zai dame 1 by 2 ko?
1 by 2.
To kun ga za mu iya multiplication dot product din 1 by 2 da kuma already 2 by 1 din already.
Yes.
To kun ga sai mu kawo b din mu plus b din mu. To shine aka yi transposing din wannan. That is yawa sai aka transposing din shi saboda if it is vector we can transpose it and do
apply dot product.
Apply dot product, yes.
Yes.
I don't know, ban sani ba ko an gane abinda yanda muka nemo t din nan. Muka nemo abin nan. So kun gan shi nan W1 times X1 plus this plus B. So wannan saboda multiplication ne this times this, but dam iya ne mai da shi dot product. Idan muka mai da shi dot product is still something mathematically. So that's why muke da W power T times X plus B. So still in the book sun yi explaining din wannan that this is dot product. Can you see that got transfer, something like that? But you will see this a lot in you see this a lot in machine learning or deep learning later. If we move on, you see it a lot. So what I'm saying is just be aware why we do the transposition. So I believe now we know how we can now how we get this expression. How do we get this expression? Just to recap, is we use get the input, our input, which are the futures, we multiply by weight, this by weight, and get the output. And these weights are something that when we are training machine learning model, what we are always trying to learn is this weight. Because if you remember, this X is your future. So for example, I give an example, these are the future, this, and they want you to predict class Setosa. So it means in machine learning, you will be getting the futures in deep learning, but what are you going to learn that will make your prediction, we predict Setosa exactly? So this is what we are going to be learning always, our weight and bias. So weight, weight. We update the weight always. We predict, we do something, and so X is will always be given X, and the weight is something that we always iterate to find the best one. Anyone with question before we proceed? Any question? Yeah, as I said, today the class is just this, the chapter of the book is just trying for us to lay some foundation. I think from next chapter, we'll see the hands-on practical. But even today in this chapter, we'll try to do implement this perceptron using Python, also using Pytorch. So let's move on. So general notation of single layer neural network. So this is what I already show you. So if we have, remember, we get our intuition of biological neuron with artificial neuron. This is biological neuron, right? We have salivary, we have dendrite that receive information, we have human axon, we have synapses. Then we say, okay, maybe artificial neural network can be this dendron. These are the input we have. That is your future. You have artificial neuron, you have activation function, and you have your output. So this is it. So let's look at how we can implement that. So you can see this is the input, X1, X2, and you have your weight at W1 up to WM, right? And you have a bias. Remember, I told you we added something at bias, because bias is not from your future. So these are our future if we are given data set, this, but bias is not given, right? So bias is something that you just add to the model. Maybe we can say bias is 1. That is what we do. We add bias maybe as 1. And here is our activation. So activation here, it means here, this is summation. If you remember in mathematics, this is summation. We sum everyone here. That is W1 times X1 plus X2 times W2 plus XM times this plus finally B. That is the summation. Then we apply activation function on top of the summation and to give us the output. So the activation function here will determine, will it be 1 or will it be 0? If the summation, the result of summation is greater than 1, as we saw here, if it is greater than 1, then the output will be what? 1. If it is less than 1, greater than 0, it will be 1. If it is less than 0, it will be 0. So this is this activation. Then we have our output, which is Y hat, right? Any question? So you can see here, we said, because here you can see X1 up to XM. So when we do summation, remember in our mathematics, we say summation from I equals to 1 to M, sum this, XI, WI, XI, X1, W1, X2, W2. Can you see that summation plus B, which is, can you see mathematically? Then mathematically this, then this activation function is now applied to the total of the summation. Can we see that? But this summation can be represented as a vector, right? So here we use X power T W, X power T, that is the transport. Now we apply this. Now this one will give us our Y hat, which is a result prediction. And now we determine if the Y hat, the result, if the result of this, that is the result of this, is greater than, is less than or equal to 0, then it is 0, the output. Then if it greater than 0 is 1. Yeah, any question? Malama, yau irin yau abun ku muke na lissafi. Malama, ki saka hannu idan ba mu yi ba daidai ba. Yeah, any question? Yeah, so you can see, however, often inconvenient for mathematical notation. So sometimes this notation is not convenient because maybe we say plus B, we always add B, and yeah, so sometimes there is remember here we are using standard perceptron is 0 class. So it's predicting 2 classes perceptron, 0 or 1, kokuma black and white, 2 class. So that is why we have this. Sometimes this bias unit is not added. Sometimes what is happening, sometimes you see that it's not added to this, is as your input X1, W1, x2 w2 x to this, we use 1 as your bias. So we fit in 1 to your model as just the bias, right? You just need to add and use another w0. So you can see here we started with w0, not w1. So here this is another way to represent bias. So they are still the same thing, but in some text, in some book, you see that they added 1 to your input. So don't be confused. When 1 is added to your input, it is just the bias. So that is what we mean by this. So you can see here, we said I from equals to 1 to m, but you can see here we said I from 0 to m. Can you see that? And now since we now remove the bias here, because here we have our bias here, that is why we have xiwi plus b, that is b is a bias. But now we don't have the b, we don't add b here because we use 1 as bias, so it's input here. So now here you can see we can say xiwi only, so you can see these are bias. So this is basically 2 different notation you may see in the book. But one thing with this notation, as they said, is that if you have your input, one issue with that is that, for example, one issue with this is like if I have my features like this, my features like this. If I have my features, for example, x1, x2, x3, up to xn, right? The problem with this notation is that sometimes if you have if you have 1 to be one of your input, it means what you need to do is like you need to shift all your input. So what do we mean by this? We need to shift our input to contain 1, then x1, x2, up to. So it means we need to shift our future vector to accommodate the 1 here as a bias. So this is also computationally expensive sometimes to do the shifting. So it's just like just telling you like there are different ways to show the bias. So this is something, yeah, you should know. This is something that I've been showing about our future. So if you are doing machine learning, you'll be given your futures. We already know this is our futures. These are the class we predicted. Yeah, any questions? So this is basically because perceptron is 2 class problem. So this is, for example, how deep learning classification works. So is this cat or dog? You are asking question. This is something here inside. Now it will go into input layer, and now this activation neurons, and now you have some kind of output layer. It will say this is dog or whether it is cat. Okay, let's look at now how we can implement perceptron. Now let's look at, still we are gaining the intuition of how this perceptron works, which will extend it to deep learning. Remember, we are still at chapter 2. Assume we want to use perceptron for binary classification tags. Here, for example, we have, oh, no, this one, let me see, oh no. Okay, so assume here we have a data set here. You can see we want to classify it. You can see this is blue. Which color is this? Which color is this?
Gray.
Okay, so what is happening here is that perceptron, as I said, is 2 classification problem. So you can see here we have iteration. Now it started from 3. You can see that it's trying to classify the data. Now you can see now it is here. Now iteration number 10. You can see it's trying to do some kind of classification. Remember now here, this is blue. When it is blue here, you can see how it wants to classify this perfectly. Now let's look at what is happening in the learning. So this is very important for us to learn, to know how machine learning works. Now we all understand this is our x1, x2, xn, our input, and this our weight, right? X weight, w1, w2, wm, and this is our bias. Now we sum all this one and input into summation function, right? And now we input threshold function. This threshold function is this. that we have already said. This function, can you see that this one? Can you see that? So you can see that x1 up to this times this plus this times this plus this times this plus bias. We will sum them. Now after we summation, then we perform this activation function on this summation, which is this, right? So this is what I mean by here. So you can see this is it. We separated. Now we do the prediction. So you can see from threshold. Threshold is the one that determines what will be the output, right? Which is y hat, which is class will be 1 or 0 or 1. So this is our prediction. We know this is our prediction. Now, if this is our prediction, assume that we want to do classification whether something is dog or cat. Now we now do the prediction, which is y hat, but the prediction is not correct. Now, how can the machine? How can we do learning, right? Now let's assume that you want to actually learn how to drive a car, right? Now if you just start driving and it happens that you just bang at a building, right? Now when you bang at a building, it means you have not learned well. The next time is start the car, right? Start the car and now move again, looking at update your knowledge. Oh, when I see this, I should not bang this. This is a building. Now I should update my knowledge so that I can move to different direction. So this is what is happening in machine learning. This is a central idea, this idea. Now, this is your input. You have your weight. These are the weight. I said this weight are something that you learn that will shape your understanding. And this weight, how do you initialize this weight? We initialize them sometimes 0. They start from 0. So if this is some minimum, what I mean by 0 is some very small number, 0.1, 0.2, 0 point something. I will show us something. So here we can see x1, w1, we do multiplication, and now we have the output. But it turns out that we say, oh, the class is 1, but we said the class is dog, but we say it's cat. Now, how can we update our understanding so that next time we do what is called update? Can you see update? Now, what will happen in the update? This is the real class level. The real class level is dog. Okay, but when we do the prediction, we say it's a cat. So you can see it's wrong, right? So what we need to do is we update our knowledge that, when you see this, so we update our knowledge. So this is the knowledge, the prediction output, and this is the real value. So what you need to do is the prediction is some numbers, right? Maybe you predicted is some numbers, and this is the class level. So you find the error based on class level and the prediction. You compare them and find the error. Now, when you find the error, now you go back and tell this weight. This is the error. This our previous prediction is wrong. This is the error. How can you update this weight so that you will reduce this error? This is how the learning works. It's essentially, how can we update this weight and so that our error reduces? Now, what you need to do is update this weight. You are not going to do anything. Update this weight and now move again and go through again. Now do the output. Oh, you again miss the classification. If it is like a regression, I mean, yeah, maybe let's assume it's class and dog. Still, you see that it is class, and instead for you to say it's a dog, you say it's a cat. Oh, you compare with this, and oh, you minimize the error. If the error previously was 10, now you minimize the error to be 6. Now you tell this, how can you minimize? This is the error. Now the error is 6, not 10. How can we minimize? So they will minimize, they will change this weight. If they use 0.35, now they will use maybe 0.21. They will now change the weight and now put it. The next thing is, oh, they still predict it is cat, not a dog. Now you compare the true and this, and now the error is 1, is 0.1. Now you say, okay, still we have an error 0.1. Update this weight so that we can do better. Now update the weight, and now you predict correctly. This is essentially how the learning works. So let me show us something regarding this. Let me see if I have that. Okay, okay. Any question before we move on? Anyone with question? Valalu. Okay. Right. So can you see my screen now again? Can you see my browser?
Yes.
Hello. Okay, now this is something. So let's look at this. This is a data. I want to just tell us. This is from Google Playground TensorFlow. Playground TensorFlow. How this? So this is a data set, and this is our input. So you can see this is the data, and since this is a data, this is a data, and we can see that we have some features of the data. This X1, it represents some kind of vertical lines in the data set. Can you see that? This X2, it represents some horizontal. Can you see when I put it, something changes in the data and the output? Can you see that? Here, if I put it, can you see something changes like vertical? Can you see this is like horizontal, right? Now, this is the neurons. These are weight. Can you see the weight here is 0.44? Can you see the weight is 0.30 here? Now, what I want to do is, maybe let me add the neurons. So I have 3 neurons. Can we see the neurons? What I want to do is, given this data, we can see this is not separable, right? We want to use neurons to classify this data to make it separable, to show that this is a 2-class problem. So I select classification and no regression, noise. I add noise. Maybe the noise is your bias, some stuff like that. And now maybe let me batch size, maybe something like that. So let me, you can see this is how it works. Now let me play this. Look at the test loss. Can you see now, using this, your input, these are the neurons, these are the classification. So you can see now this has classified your data. It classified, it circled this, that this is one class, this is the outside is another class, right? But this is loss, this is the training loss. Can you see it's 0.0? This training loss is something that I was telling you about. It's about the Y hat, which is the result. So now this is the test loss. So you can see now here it do that. But if you look at this one, can you see the weight is 1.3 now? Remember before we start, the weight is 0.34, right? Can you see this is 0.85, different weight? Can you see? Can you see 0. Can you see? Now this one also neuron, can you see the output weight to the last layer? Can you see that? So this is something just to show you, but there are more to that, but just I want to show you how this learning works. So this is another data set, for example. So you can see this one is difficult to classify. So we want to classify what is blue, what is this. So now let me add some neurons, and now we want to do classification to classification, and let's do this again. So can you see it does the classification? Now it can you see it classify this? This is class. Can we see that? So this is something that to help us understand the intuition of what are these. Hello?
Doctor, can we add a layer, hidden layer?
Yes, you can.
Deep learning.
Yes, this is perceptron. Yes, that's a good question.
Yes.
So this is perceptron, just trying us to understand. Let me share. Okay, yeah. So what are you saying? Yeah, me,
I said, can we add a hidden layer, because what we have here is neural network. Can we, if we add a hidden layer, we make it deep learning, because what we have here is
yes.
artificial, yeah. So if we add a hidden layer, I know we can make it to be a deep learning. I said, can we add hidden layer to this?
So yeah, so you can do everything. Let me just show you. So you can even try it. So there are a lot of stuff that you can do. For example, step function that I showed here, activation function. You can add noise. If you say you don't want to add here, you can see that. You can select the activation function, whether ReLU or whatever. You can say, okay, I want to do regularization L1 or L2. If you want to do regression, you can select that. For example, here you can add this. You can see here I add another hidden. Can you see that hidden layers? Can you see that neural network? Can you see that? So this means that when we do want to, okay, so let me select this one. Let's make it deep neural network. Can you see that we have this, hidden? So you can see this is difficult to classify, right? Because it's something calculated. But let's look at it. The neural network will learn it. So let's look at it. Look at the layer. Let me stop it. look at the test error before 0.5. Look at the training error 0.4 means it's good error. He hasn't learned. But let's start when we start training. This is the epoch. So let's look at it. The epoch, it means the so you can see the training error is 0.32. It now reduced 3.1. Can you see that? Goes back. Can you see it's trying to yeah. So that is just basically the intuition. You can try and select different data sets. For example, here, and add the neuron. You can see here we have 6 hidden layer, right? 1, 2, 3, 4, 5, 6. Can you see that? So there are a lot of stuff you can read it and try to see what it means. Yep. Okay, let's move on. Okay, so do we understand this? So you can see this is the error that we update our weight and stuff like that. That is how it works. So any question before we move on? So how this update works. So this is it mathematically. Now, if I have my X, which is a point, and it is prediction, X2, it is prediction, X1 prediction. Now, how do we do that mathematically? Initialize your weight to be some value for every training epoch. What do we mean by epoch? Now, epoch means when we train from here and go and do one prediction, and we understand it's not correct, this single forward pass from your data to do prediction is called a one epoch. You go back, update the error, update the weight, and do another prediction. That is second epoch. Go back, third epoch, fourth epoch, fifth epoch. So you can see that we can have 20 epoch before we reach a good accuracy. Remember the other one I showed? Let me still show the screen for the example I showed. Okay. Yeah, can you see we have epoch? Can we see epoch here? So when I want to train here, epoch, can you see like the epoch? So this is moving fast. Can you see that 200? Can you see that this is the epoch? Like it is training from here to here, that is the epoch. So if we reduce this guy, okay, no, we have this. So if I have this data set, now I say, okay, do the classification. Oh, here I'm also using regularization. I should haven't even done any regularization. Let me give ReLU. Let me. Oh, I removed activation. Anyway, yeah. So what I'm trying to say is that you can see this is the epoch. That is the number you do from here to go to the next round. That is called epoch. So this is how we do it. For every X and its prediction, for every X and its corresponding true level, find the prediction where we use this. And now this is the error. Prediction, Y, you can see this is the prediction, right? Yeah, Y hat, and this is our true level. So what we mean by this here is find the error. When you find the error, update your weight. Remember I told you here what we are doing, we are updating our weight. How do you update the weight? New weight is equals to weight, that is previous weight plus error times Xi. That is, if you want to update weight, what you need to do is the error times Xi, that is this Xi at that position. Then you are weight the previous weight. So this is what will happen. So weight plus error times weight. Then you go another round of epoch. So this is how the learning works, the prediction. So yeah, anyone with question? But if there is no error, then no update. So is example, if we don't have any error, that is the prediction is correct. So you can see here the true and the prediction, no error. If there is no error, this means that here will be 0. Can you see that 0 times xi? So therefore, your previous weight is still the current weight, right? So no update if there is no error. So this is what happens. Any question? So this is what happens, how we do the perceptron. I think it is time for prayer. So today we started late. What we can do is the next thing I want to do to show us in this chapter is implementation of this perceptron in Python and Pytorch. Implementation of what we saw now, like this stuff, to just get the intuition, is what we'll discuss in Python and also in Pytorch. So now it is 3:57. It's time for prayer. I think a lot of us are here. We will stop here, and we can, tomorrow's session, we can do the practical implementation, coding example, using implementation of this, using Pytorch and also Python. What we'll do will actually, especially for the Python one, will actually seal our understanding on how the perceptron works, especially following this one. So if you understand this, when we come to deep learning, you say, oh, this is how to update the weight. This is how to find the error. That is the original minus the prediction error. Then this is how to find, the prediction, which is y hat. You apply this, which is this, So this is it. Any question? Any question? Malama, any question?
No question, Doctor.
Zaradin, how are you?
Lafiya lau, Doctor.
Ana tafiya jin an fara bubbuga ko?
Ana ta yi, ana ta buga.
To, masha Allah, masha Allah. Alhamdulillah, wala muna ta bubbuga mu ma.
Allah ya taimaka, Allah ya taimaka.
Amin, amin. So, yeah, please read the chapter 2 of the book and try to see what you can understand. Tomorrow, inshallah, then we can see the implementation of perceptron. This is really, really important, the implementation, especially for the Python, to show us how the learning works, how we do some learning. Also, we're gonna do some kind of classes. I believe we all, anyone with issue with classes in Python, if you have issue, let me know so that I will assume, because we already did classes and so in our Python learning, because what we'll be doing, we'll be seeing how classes work, how definitions work. So if you have issue with classes, and just let me know so that maybe we can have a separate session for with other people so that I can take them to classes. And because if you don't know what classes are, how to do, then in the when we go to Pytorch and stuff like that, you may be a little bit confused. So let me know if you have an issue with classes and basic that I can take you. Yeah. All right. So I think we can stop here if there is no question, and inshallah we can meet tomorrow to continue with the session. Batambaya.
Thank you.
Falalu, any
Thank
question?
you,
Okay. So thank you all. See you
Thank you,
tomorrow,
Doctor.
inshallah. Be salam. Bye bye.
Thank you, Doctor.
Okay. See you. Bye bye.